What's Gucci, everybody? I wanted to remake my video on Big O notation. Let's get started. So, Big O notation, according to Wikipedia, is a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. So, Big O is the trajectory or the pattern the function or algorithm takes as its size approaches infinity, not exactly how many seconds the algorithm takes per maybe the size being an exact number like 100 per se. Okay, now there are a few Big O categories. Now here I want you to remember that n represents maybe the size of your algorithm. So you could imagine for all of these categories, you have an array of size n. And in that size n, it could vary between 100 elements and then get bigger and bigger and bigger. And as you increase it, the time of this algorithm may increase quadratically or linearly, okay, or exponentially, based on the algorithm you're running on your data set. And that's what n represents, your data set size. Okay, the first category is constant time. That means no matter how much you increase n, your size, it remains constant. So maybe no matter what in your array, for example, you're always checking the first element. So maybe the first element of the array is either, maybe the size is 0, maybe the size is infinity, but you're only checking the 0 index in the array, and it's constant time. It always takes the same amount of time regardless of size. So size does not change a constant algorithm. Logarithmic is when you split your decisions split by half every time regardless of the size, at least log base 2, but if it was log base 3 or log base 10, you just say logarithmic. So an example of a logarithmic algorithm is a binary find. So if an array was sorted, for instance, if you were trying to find an element using the binary find, it would take you logarithmic time because you're always splitting, right? So if you have 100 elements, you would pick like the 50th, then the 25th, then the 12th. You're always splitting your choices in two. That's how you can think of a logarithmic algorithm. You're eliminating half your choices every single time. A linear algorithm is probably the one you're most accustomed to. It's simply a loop. So based on size n, you're looping through n elements. A log linear algorithm is, again, combining the two. Okay, so taking the past two examples, it would be like maybe you're running a binary find on n elements, so that for every n element, you're running a logarithmic algorithm, which is the binary find. So it would be, you would have a loop, and then inside the loop, you're running maybe a binary search. Okay, the second is quadratic, which is a linear times a linear algorithm, n times n. And so, for instance, that would be a loop within a loop. Many sorts, like the selection sort, are quadratic time, and that's n squared, n times n. Cubic, and just to show, usually there's not many cubic algorithms, but maybe, for instance, sorting a 3D array where you have an x, y, z coordinate system, looping through all coordinates would take 3 loops, a loop within a loop within a loop, and so that'd be cubic. And obviously you could have n to the 4th, which would be 4 loops within each other, and then, you know, a lot of times you don't need more than 4 loops, but you can see this would go on forever. And now examples that are incredibly slow or incredibly computationally expensive is exponential and an n factorial algorithm. So an exponential algorithm, 2 to the n, remember, you're switching, unlike quadratic, you're switching, the n is now in the power position and not in the base position. So 2 to the n would, for instance, be maybe many recursive algorithms. For instance, like the Fibonacci algorithm, where every call creates 2 additional function calls. If you've done the recursive Fibonacci before, that's a exponential algorithm, very computationally expensive. And then the n factorial algorithm is when, you know, every function call, has n minus 1 function calls associated with it. So it goes up crazy quickly. And an example of that would be the traveling salesman algorithm. You can look at the Wikipedia article for that. I won't explain that in detail here. Okay, again, this is an example, an actual code example of a constant time function. Int sum equals 5 plus 4. Note there's no array or size to be taken into account of, right? It's just a simply algorithm. No matter what was around this, what array you had passed into it, it would simply always just add 5 plus 4. An example of a linear algorithm here is a loop. I made it a little bit more complicated. So in this case, we'll go looping through the A array. We have an if statement in the A array, but what matters is the time it takes, which is the amount of looping we do. So this is a linear algorithm, n. This would be an n squared, a quadratic algorithm, because we have a loop within a loop. In this case, the size is n, right? Literally the lowercase variable n. Okay, and then big O can also be named as asymptotic complexity here. And I just want to show a more complex example, but literally all I did was combine the last three. So here we have a big O of n squared plus n plus 1. So I have my double for loops, and then we have that single loop I showed you, and then we have our constant statement. And so a very exact way of writing the asymptotic complexity, or the big O, would be n squared plus n plus 1. But the way you would shorten that in notation is it's big O of n squared. In big O notation, you care about the worst case, and you also care about the biggest factor. So I showed you those terms before. If there was an n factorial, you would simply say this is big O of n factorial, because that term is going to have the biggest growth trajectory and take over the equation as you approach infinity. I'll show a graph at the end. Okay, and just to illustrate this even more, so I showed you these terms and showed you that as your size gets bigger, the time it takes very greatly increases. And that's what you're caring about with big O. That's what you're really thinking about. It kind of like a derivative. A derivative shows how fast the equation is growing. So I put in for each kind of type here, for each equation type, what would happen if you put in size 100. So if you see constant, obviously n doesn't affect constant time. Logarithmic, it's 6.64. Linear is 100, n is equal to 100. Linear logarithmic is those two multiplied by each other. Quadratic would be 10,000. Cubic, 100,000. Exponential, a number I can't even pronounce. And factorial is a number way beyond exponential. I had to change the font size. You can see how big it is. So you can see how quickly the time complexities grow for the same input. That's why it's important to try to make if you can possibly figure out a more efficient way in your algorithms, and this is what people ask in interviews, to make your equation, and change your equation from quadratic to logarithmic linear, you can see how much time, how much complexity you would save. Okay? And so, again, visualizing big O is very important in my opinion. So when you talk about big O, you're talking about the worst case, meaning the biggest term that takes over your algorithm. And so the reason you're talking about big O is because you are concerned about its growth. Maybe it doesn't take a long time, like at the beginning of our graph here, you can see the white lines all kind of meet together, so you won't know the big difference between a quadratic algorithm, for instance, and a linear algorithm when the size is only 5. But as you approach thousands of elements, hundreds of elements, like the accounts on Facebook, for example, you would notice a huge time delay in your algorithms. And that's why big O is cared about a lot in interviews in Silicon Valley. It shows you understand what if you were able to, if you scaled up your project, maybe you would have a huge time sink problem that you don't see with with limited testing, only testing a few elements. So that's why it's very important to understand big O. I hope you enjoyed that presentation. If you have any questions, please let me know. Link and subscribe, do all that stuff. Have the best day of your life, everyone.